The Rockies are right over there. Don't just go to the conference. Go and see the Rocky Mountain National Park. Go hiking up at Bear Lake or something. Don't do what I did, which is just to come for the conference. Go and see the area.
Good morning. This is Back to Basics Rule of 5, in case you've possibly found the wrong room. I'm Andre Kostur. I've been working in C++ for nearly 30 years. I was mostly responsible for introducing the language to my previous employer. Most of their products are now based on C++. Since then, I moved on to Arista Networks. Shortly after I joined there, I added in a C++ users group for the company to help educate all their people to raise the level of bar of C++ in the company. This is my second time speaking at CppCon. Last year I did Back to Basics Resource Acquisition is Initialization. Feel free to check that out after this talk. We're going to be talking about some basic features of C++, and I don't want to just list the rule of 5 and say, here you go implement, we're good. I want to spend the time to develop how the rule of 5 came about so you understand where it comes from. So first, to the agenda, I'm going to give a little bit of background. Since this is one of the core guidelines, and as far as I can tell, none of the other talks this week are talking specifically about the core guidelines, I'll say a few words about that. Then we'll be moving on to talking about the rule of 5 specifically, develop all the considerations we had leading up to it. We'll take a slight sidetrack in talking about the compiler-provided functions, because those are the ones that cause us to have to think about the rule of 5. And then I'm going to talk about the rule of 0 at the end, close to the end anyway, because rule of 5 is good, rule of 0 is better, and we will see why. So there's a little bit of background. C++ is a value-based language. It inherited this from C. If you don't say anything different, when you pass a value into a function, for example, it's passed by a value. In C, they try to do something resembling pass by reference, except they call it a pointer. But what you really do is you take your address of your variable and you pass that pointer value into your function. So we're still a value-based language. In C++, we added in references, which make that easier to deal with, but you have to ask for it specifically. So I would argue it's still a value-based language. In addition to being just a value-based language, C++ has a well-defined object lifetime model. We know when objects start their life, we know how long they live for, we know when the object ends its life. This is where constructors and destructors come into play. C++ is not a small language. Given that we spend a week talking about many, many C++ topics, and let's be honest, we haven't even scratched the surface if you listen to all the talks, there are many things to keep in mind when you're writing your code. This can be daunting, both for beginners and even the experienced people, that they have to think about a lot of things. We need something to make this easier for ourselves. So the community, edited by Herb and Bjarne, have come up with the C++ core guidelines. Bjarne mentioned them some in his plenary talk, and you'll hear a few more times in passing at least. But essentially it's a long list of good ideas, guidelines, some guidance for people to follow when writing their C++ code so they don't have to try to derive everything from first principles. This covers everything from what should you choose, how should you choose to pass variables into functions? How should you declare variables? Should you use RAI? Spoiler, yes. Easy answer. But it talks about, never use naked new and delete. Of course, these are guidelines, so you will have that whole your mileage may vary thing going on, because much like every rule, there's going to be an exception to everything. But since we're talking core guidelines, the rule of 5 is one of those guidelines. Specifically, guideline C21, because the core guidelines is developed into sections. Bjarne listed some of the philosophy section in his talk. This one comes from the design of classes. I'm not actually going to define what the rule of 5 is right now. So what I'm going to do is I'm going to walk through and look at all the considerations and scenarios and issues that crop up if you don't start with the rule of 5 in mind. To do this, we're going to look through a simple string class. It's going to be like standard string, but worse. It's going to be a dynamically sized string. It'll have no small string optimizations. This will be slideware. I'm not going to claim that most of this code is anything resembling good code, but it will be at least functional. I'm also not showing you all the other bits and pieces of a string class. Starts with, ends with, find. The member functions we're not really interested in for the purposes of this talk. I'm more interested in what we're going to refer to as the special member functions. Your constructors and your assignment operators, destructor, that sort of thing. Since it's slideware, there will be simplifications. Things like I'm going to be using struct instead of class. Everything's going to be public, largely to make sure everything fits on a slide. So, simple string class. I want to construct from a standard C array, string literal. This is what we get to start with. We have a constructor, takes a char const star, allocates sufficient memory for the string you passed it. Remember the +1s, you don't forget the null character. String copy, whatever other interesting features we want, and a char star. Of course, we are ignoring the little detail that there's no RAII here. I've chosen this intentionally. What if I write code something like this? I've instantiated one of these simple strings. I've initialized it with a reasonable value. I do some operations on it, and the scope ends. What happens? Well, sorry?
Memory leak.
Memory leak. Very much so. Remember, I've allocated memory. Where's the delete to go with this? That's one of those voices that screams in your back of your mind eventually. I see a new, where's the delete that goes with it? So I'm going to need to do something at the end of the lifetime because I need that memory to go away. That's okay. We know how to take care of that. Define a destructor, delete square brackets, not delete square brackets because we allocated an array. Great, now we can allocate these objects and they'll go away nicely. Very nice. But what else do we need to consider? What happens if we start using this class a little more sophisticatedly? I have a function, takes in one of these simple strings by value. Then I construct one, do whatever operations, build a string, add more stuff to it, pass it to some function. Pass by value. It's going to make a copy of my class. But what's the compiler going to do to give me that copy? Of course, it's going to copy the pointer. The pointer's holding dynamic memory. Now I've got two objects, same pointer to the same allocated memory. When some function ends, that val parameter is going to go out of scope. We just wrote the very nice destructor to take care of the memory. Yay. Hit the end of this function and your sanitizer starts going insane because you go and try to delete that memory again. And that's even assuming you don't try using S after some function and before the end of that scope. Because of course the memory has already been deleted. So now we've got two problems. We've got potentially use after free followed by a double deletion. Okay, but we can solve that too. We can provide our own copy constructor. So now I can teach the compiler, here's what it means to properly copy one of these objects. So, initialize data with a new memory, like still remembering that extra null character at the end. Copy the data, excellent. My object now knows how to copy itself properly. That way, when that val goes out of scope, it'll delete its own memory. S still keeps its own memory. We're all good. And remember, simple string, I'm not trying to do anything fun with copy and write or anything like that. Okay, that's reasonable enough. How about we move along a little further? I've got two strings. I have a source and a destination. I manipulate source by some whatever mechanisms it has. I try to assign source to destination. Remember, I still haven't defined what copy assignment operator is, so I get the compiler provided one. What's the compiler going to do for me? It will assign all of the member variables. My member variable is a naked pointer, so it's going to just copy the pointer. Okay, now we got a couple problems. The pointer I just copied over was pointing at valid memory. It didn't get destroyed, it was copied over. So now I've leaked, I have a value. And I just copied the original pointer, so again, I'm back to, I have two objects pointing to the same dynamically allocated memory, and both objects will correctly delete the memory for certain definitions of correct. Okay, we're back to that double deletion problem. At least we may not have the use after free because these two objects are going out of scope at pretty much the same time. Okay, we need an assignment operator. Now, this assignment operator may look a little bit on the complex side, mostly because I'm taking into account that if the new throws an exception, I haven't ruined my source string. So that's why I do this new off into a local variable, do the copy, swap the pointers, and then delete that now local variable, and return this. So now my object knows how to copy itself, it knows how to assign itself, it knows how to destroy itself. And before C++11, this is where the story ended, and we'd be talking about the rule of 3 and not the rule of 5. But we got lots of very useful information, lots of new tools in C++11, including move semantics. What does it mean to move objects around? Because we have dynamic memory. Dynamic memory is slow, relatively speaking. Wouldn't it be nice if I can just move the pointer along? So let's look at that case. I have a string, it gets constructed and does all of its good stuff. Then it is about to be passed into some function, and I explicitly move it into some function because I want to save this extra memory allocation and data copy. That might be multiple megabytes of string that we're copying around. I don't want to pay for that copy. Well, we have a number of scenarios at play here, because it all depends on, have we defined the other functions yet? Because if I've defined none of the other special member functions, if we're back to the beginning, we have only the constructor. This gets you the compiler-provided move constructor, which will try to move each of your member variables. Okay, the move on a raw pointer, there's no special thing, no savings on moving a raw pointer. So the compiler will give you a copy of that. And we're back to the problem we had with the copy constructor. Two objects pointing the same memory, they're both, in this case, they wouldn't get deleted because we don't have a destructor yet. So that's the first scenario. Second scenario, if we have added the destructor, by adding the destructor, the compiler no longer provides you with a move constructor. We'll look into more details on that in a few slides. Which means it'll default back to copy. But since we haven't provided a copy constructor yet, we're back to the copy problem that we looked at a few slides ago. Not good. Okay, if we have provided the copy constructor, like we did a couple slides ago, that also takes away your move constructor. But that's okay. Based on the reference binding rules, if I have an R value reference, I have no move constructor, so the compiler will look for something else it can call. It has the copy constructor takes a const ref to the string. You can bind an R value reference to a const L value reference. So that will call your copy constructor. So now it's going to copy this correctly. But remember, we're trying to move, we're trying to save that extra memory allocation, save that extra copy, and ideally, save that extra destruction. So if we've only added the copy constructor, we at least get the right copy, but we get memory leaks. If we have the copy constructor and the destructor, we're still not horrible. We are at least still getting a copy, but now we're paying for the extra costs of copying this thing when we were trying to move it. Okay, so we need to add another function. Here we go, we have this fine move constructor. It's even no except, so it plays nicely with things like stood vector. Copies the pointer, and specifically reaches back into the source and makes the source pointer null putter. Because remember, delete on a null putter is safe. It's a no-op. So now my destination holds the memory, the source holds nothing, we're all good. Assuming the rest of the class knows what to do with a null putter as the data member. So you move construction. How about move assignment? We're going to run into the same problems all over again. You'll try to move, there's no move assignment, it'll fall back to the copy assignment operator, and then all the consideration we just talked about applies here. So write a move assignment operator. This time I don't have to worry about playing with a local variable because delete can't or at least shouldn't throw, and the rest are just assignments. So no exception possibilities here. So here we are. We started with a nice simple struct at a single member variable, pointer to char. And in the meantime, I've had to come up with 5 new functions to deal with all the little considerations of what that member variable isn't doing properly on its own. It doesn't have to be memory, it can be any other sort of piece that needs special consideration. So now we can finally get to what is the rule of 5, formally speaking. Rule of 5 C21, if you define or equals delete any copy, move, or destructor function, define or delete all of them. And I've listed all 5 there. Destructor, copy constructor, copy assignment operator, move constructor, move assignment operator. Essentially, if you have to do something special in one of these, you probably have to do something special in all of them. Notice I didn't mention anything about that original constructor we started with. The original constructor, its job is to get your class into an initially consistent state. That does not imply that it doesn't know what to do with itself afterwards. But as soon as we added that destructor, that started a whole cascade of, okay, now I need to worry about my copy constructor. I need to worry about my copy assignment operator. These are a lot of things to think about. Rule of 5 helps kind of shortcut that so that as soon as you touch one of them, you're immediately reminded, by the way, here, do the other 4 as well. Say something about them. Now we'll take that side trip into compiler-generated functions. What does the compiler do if you don't supply the functions? A couple years ago, Howard Hinnant came up with a very nice chart of if you provide this function, what does the compiler provide for you? Thank you, Howard. There's this lovely special members function chart. I know of more than one person who has printed this out and stapled it to the side of their workspace because they always need to remember which of these things has been done. If you look down the left side of the chart, it has the names of the various pieces that you may have declared. Did you provide nothing? What happens? Did you provide any other constructor, like the one we did for simple string? What happens? And across the top, it talks about what does the compiler generate for you. So where we had started was that second row. I provided some other constructor. The compiler has taken away the default constructor. Note they're not declared. And all the rest of the ones are implicitly declared for you. The compiler will do what it thinks is right in all those cases. But do note that there's dark blue cells, green cells, light blue cells, red cells, gray cells. There's a lot of details and crunchiness in this chart. It's a lot of details to have to remember. The rule of 5 deals with this portion of the chart. We're not worried about the constructors, and we're not really worrying about the default constructor. They'll do the right thing. We're worried about this corner of the chart. That didn't solve my complexity problem. You still have all those same colors in there. Rule of 5. If you apply the rule of 5, instead of having to worry about that entire lower right, somewhat larger than a quadrant of the chart, you worry about that diagonal. You just supply all 5, if you need to. So all those gray, green, red cells aren't that important to you anymore. Wouldn't it be nice if we could actually leverage what the compiler generated for us instead? A little bit of a shortcut, this is what the compiler does for you. If the compiler is providing for you a default copy constructor, it is essentially going to turn around and copy construct each of your member variables in turn. And if one of your member variables isn't copyable, it will also take away your copy constructor. The poster child example, stood unique pointer. You can copy it, you can't move it. So if you have a unique pointer, your class won't be copyable, but it will be movable. If you have something like a std mutex, you don't get either of them because much like the copy constructor, on the move constructor, if you don't provide one, the compiler will try to move each of your member variables. You can't move a std mutex. And worse, you can't even copy a std mutex. So you actually get hit twice with a std mutex. It takes away your move and your copy. Because remember, if the move can't happen but copy can, move essentially falls back to copy. The details are that reference binding trick I mentioned earlier. Same stunt with the copy assignment operator, move assignment operator. If you don't provide one, the compiler will turn around and just move assign each of your member variables in turn, in the order in which they are declared if you want to be picky about it. And I mentioned that order because finally you get to the destructor. If you don't provide one, the compiler provides one for you. And it will destroy your member variables in the reverse order in which they are declared, which follows the standard C++ model. Construct in one order, you destruct in the exact reverse order. So, given that we know what the compiler is going to generate for us, can we change our string to use an appropriate class to maybe, can I get the compiler generator wants to do all the work for me? I have some memory, I want it to copy properly, move properly, destroy itself properly. I know, I'll reach for shared putter. Remember I said slideware earlier? I was even diligent enough to remember, well, when you're doing a shared putter, I need to do char square brackets so that later on, when it gets destroyed, it will delete square bracket them. So, will this delete itself properly? Sorry, will this destroy itself properly more correctly? Sure. Object goes out of scope, shared pointer goes out of scope, releases the memory it holds. Excellent. Will this move itself properly? Yes. Shared pointer knows how to move itself. We're still in perfectly happy, safe places. Will it copy correctly? There's a question. And really there's two answers. Yes, it will copy correctly for certain definitions of copy. Because while it does copy the shared pointer, all it does is increase a reference count. I wasn't planning on writing a shared simple string. So while it compiles, and for certain definitions run, it's not correct. Call this a cautionary tale of don't reach for the first thing that happens to make your code compile. And with a corollary, shared pointer is probably not the right shared pointer, smart pointer to reach for in many, many cases. It's trying to represent the wrong ownership semantics. Okay, do we have anything else other than shared pointer? Sure, unique putter. This one will give us more of the semantics that we're really looking for. Each of my objects owns the memory it holds. Unique pointer is the right way to represent that. Back to my questions. Will this now destroy itself properly? Yes, unique pointer is quite happy to delete square brackets, the thing I gave it, because I instantiated it with square brackets. Will it move itself correctly? Yes, unique pointer knows how to move itself. It'll transfer the ownership to the new class. It'll null itself on the way out. We're good. How about copy? Copy, we've got a problem. Unique pointer represents unique ownership. Copying it goes completely against that idea. So even though I've got 3 of my functions covered for me, the copies are going to give me trouble. Okay, so now I need to provide copy constructors. So this copy constructor should look pretty close to the one we had before. New my memory, copy from source to destination. Note that this time I have to do that .get on each of the variables because those aren't raw pointers, those are unique putters. I need to reach into them, get the raw pointers out of them so I can copy the data back and forth. And again, I need to do it again for copy assignment operator. The nice thing here is I don't need to delete the memory because when I do the .reset on the member variable, that will release the memory it's holding first and then take the new memory that I'm handing it. So it plugs the memory hole problem. Copy the data with the .gets, return. Excellent. We've done all our moves. Are we in a happy place? No. Let's recall back to this chart. If I have provided a copy constructor or a copy assignment function, What happens to my moves? I lose them. My class, which used to work perfectly nice, now can no longer move itself. It'll fall back to the copy that we just wrote, so at least it will do the right thing. The problem is it will do the wrong thing in a safe manner, and worse, silently. Compiler won't warn you about it. It'll just say, oh, you meant copy. But now we're paying for that extra memory allocation, the extra copy of the data, and the extra deallocation later on. So unfortunately, we have to go back and deal with the move operations again. Now, the compiler used to know what to do with a move, but now it doesn't. I'd rather not have to write that function again. In this case, I'm only dealing with one member variable, not that hard. If later on you start adding in, a dozen ints, if you have to write that function by yourself, you have to remember to copy each of those ints, or move them, as the case may be. And then later on in maintenance, someone adds a new member variable, go back. Wouldn't it be nice if you could just tell the compiler, could you give that back to me, please? And you can. That's where that equals default comes in. You can tell the compiler, I want my move constructor back. And the equals default says, please give me the move constructor that you would have done on your own if you were allowed to. And the one it would have done on its own would have been to move the unique pointer. And of course, we have to do it again for the move assignment operator, because the same problem is going to happen there as well. The move assignment got taken away. I need to ask the compiler to give it back to me. So now we've dealt with 4 of the functions. What about the destructor? Well, we still get the destructor, so it's not that your program will fail to compile. And the destructor is going to do the right thing, but it's not the rule of 5. So really, you want to ask the compiler to default that one too. Mostly for consistency's sake. So now our simple string with a REI class to hold the memory looks something like this. You have a constructor, which is all fine and dandy. You have your copy constructor, you have a copy assignment operator. Sorry, you have the move constructor, but you ask for the default one because the compiler knows what's the right thing to do. Then you have your copy assignment operator, which you needed your own. The move assignment operator, again, ask the compiler, please give me the one you gave me, would have given me otherwise. And the destructor, please give me the destructor you would have given me otherwise. Nice. Can we do better? The core guidelines covers many, many things. The immediately preceding core guideline to the rule of 5 is the rule of 0, which reads, if you can avoid defining the default operations, do. So if you can actually choose appropriate types for your member variables such that it knows what to do the right thing for your copies, your moves, and your destruction, use those so you don't have to name any of the special member functions. Now I'm going to step away from my simple string because I didn't find a nice way to represent that. I'm going to change to an extended string. So I'm going to have some type, has that same sort of constructor, except this time my construction is even easier because stood string knows how to construct itself from a C array. I'm using a stood string as a member variable, and then you can add whatever extra constraints you want to put on top of a stood string for your type. Maybe you want to verify that it is only ever initialized with capital letters or something. Whatever the case may be. But what happens here? When I copy this type, the compiler provided copy constructor is going to copy all my member variables. Stood string knows how to copy itself. Excellent. It knows how to copy assign itself. Excellent. It knows how to move itself. It knows how to move assign itself efficiently. Nice. Knows how to destroy itself. Since I don't have to mention any of those, I shouldn't. Just leave it as it is. It'll do the right thing in all the right cases. If we look back at the chart, there's a reminder. The rule of 0 lives in that area. Everything in that area is a nice, wonderfully consistent dark blue. Everything gets defaulted. No complexity. And I'm going to come close to the end with a little bit of a soapbox. code isn't just for the compiler. When you write things down, you are communicating to the future developer who's going to read that code. Keeping in mind that in 6 months, that future developer just might be you. So what you write down is trying to carry some communications to the next person reading the code. If I see code that only defines only the copy constructor and nothing else, I'm going to start thinking, well, why is the copy special, but the copy assignment isn't? And if the copy special, why isn't the assignment special? How are these two differently? If they did something special in the copy, shouldn't they be doing something special in the destructor too? So if you only provide one or two of these overloaded functions, it's going to raise questions in the next person reading it that, have they really thought about what's going on? Almost starts getting red flags in the play, they're going to start looking for debugging. Even in the case of our, where we've got 4 of them, where we had the copy constructor, copy assignment. We had defaulted the 2 moves. We didn't have to default the destructor. It would have given it to us anyway. But by only specifying 4 of them, it should kind of raise that question in the back of your mind. Well, should we be doing something special in the destructor? By putting it directly within your type, it will come out and say, yep, the destructor does the default stuff. We're good. And at the end of the day, if you specify none of them, then you're telling something else to the person who's reading your code later on. Nothing special is happening. All the member variables behave as naturally as those member variables behave. Now, on the off chance where your actual intent is, I want to write a class that is copyable, but isn't so much that it isn't movable, but it has no valid move semantics, so I want to fall back to copy. Even in that case, I would still list the move constructor and the move assignment operator, but I'd comment them out. And leave a comment in this area. I'm intentionally commenting these out to force everything back to copy. Because for whatever the semantics of your type happens to be, you want to be sure it's always copies. Sure, question.
Why wouldn't you say equals delete on the ones that say here?
So the question is, if I wanted to take away the moves, why wouldn't I equals delete them? The problem is, if you equals delete them, that means those function prototypes still exist. So the next time you try to move one and want to fall back to copy, it won't, because it'll find the deleted one. It'll come back with a compiler error. You have now made your class immovable as opposed to moving back to copy. And as it turns out, this is a convenient time for Q&A. So as the closing, rule of 5, if you declare any of those 5 functions, declare them all. I'd strive to declare none of them if you can. And at this point, I can open up to any further questions. And for the benefit of YouTube, microphone, please.
Thank you for the talk. I have a question about the default.
Yep.
Sometimes I see code that is putting the equal default in the CPP file instead of the .h. Is there any difference, or because of like reducing linking problems?
So the question is, if you have declared the prototype, you've declared the function prototype in the header, but you equals default it in the CPP file. Is there a difference? I would suggest yes. And that's probably around inlining. Because if around inlining, and it might even affect whether or not the class is considered to be trivially destructible, constructible, possibly, because the other translation units, which include your header file, won't see that it's been defaulted, so it has to assume that you're going to provide a more complex constructor, possibly. So it can't assume you're trivially destructible or something like that. Now, it'll still generate the constructor in your CPP file, because it will need something to link to, but other translation units won't figure out that you're doing the default thing, which may affect optimization opportunities.
Thank you.
So I have a question that is, it's kind of claim specific, but oftentimes I'll have like a struct that's got simple members in it, like some ints and stuff.
Sure.
And if I do not define any of the constructors, they should be default constructed. But if I try to consume or place that struct into like a std optional or something, it complains that I do not have a valid initializer constructor. So I go in and I define the struct, open parens, and I say equal default. That still fails. Why do I have to then go in and do like empty curlies to make that function when I would expect the equals default to work?
It's actually a pretty good question. We'd have to take a look at it in code. Offhand, I would have expected it to, if it's just a struct of ints, that's pretty much, I'd say plain old data, but that's old terminology. Standard layout, I believe, is the current version. I would expect that in the optional that it would turn around and, because you would probably declare that on the stack, it'll probably result in a bunch of uninitialized ints, whereas the curly braces would value initialize them all to 0. I would expect that to work, but I would probably take a look on the compiler to see what it's really complaining about. Feel free to.
It's only Clang is the only one that
it should.
does it. So, okay.
Because it would have a default constructor of do nothing because they're all ints, but it should still have a default constructor, copy, assignment, all 9 yards.
Okay. And so I guess my question really is there a difference between equals default and just open and close curlies?
There is a difference between default and open close curlies, because once you do the open close curlies, now you have a user provided constructor. And that changes some other subtle semantics in other places in the standard.
Okay. Thank you.
Yes, thank you for your talk. When would you use the equals delete for your operators and constructors?
Stud unique pointer, like when do you use equals delete? Stud unique pointer would be the poster child. I want to take away copy construction. It makes no sense to copy a unique pointer, so a unique pointer will equals delete its copy and its copy assignment, because you want to outright forbid copying. And you could do the same thing like our original question. You may wish to forbid movement, in which case you can equals delete them, because then the function will match in your function overload path. You'll choose that function and then go, well, now I can't, compiler error.
Great, thank you.
Now equals deleting a constructor.
Hey, so does defaulting some or all of these special member functions prevent aggregate initialization?
Shouldn't.
Shouldn't?
It should not prevent aggregate initialization because you're asking for the constructor that the compiler would have provided for you already. Because I think we'll have to check that it's still considered to be a standard layout.
Okay, thank you.
Any further questions? If not, thank you for coming out. Reminder, feedback and shed both for my talk and every other talk you've seen. Thank you very much.